Hello everyone, my name is Amir Hossein Dadaisade. I'm a PhD student at the University of Bristol. Today I will be presenting our work PECoP Parameter Efficient Continual Pre-Training for Action Quality Assessment. Action Quality Assessment is a method used to evaluate the quality of actions or movement in various contexts. For example, it evaluates tasks such as leg agility for Parkinson's disease severity assessment, diving form for sport performance, and suturing for surgical skill assessment. Unlike action recognition, which simply identifies what action is taking place, AQA detects subtle differences in how actions are performed. For example, in Parkinson's disease action performance scoring, one or two interruptions during a regular rhythm of a patient's movement, performing an action like leg agility, can result in a different quality score, and this is in contrast to the action recognition task where subtle or even more pronounced differences in performing an action should not affect the action classification. One of the main challenges of AQA is the lack of annotated data. A common solution to address this issue is initializing the AQA backbone with parameters pre-trained on a large action classification dataset like Kinetics 400. While better than training from scratch, deploying such pre-trained model is suboptimal for AQA because of the large domain gap between action classification and action quality assessment. The contributions of this work can be summarized in four aspects. First, we propose PECoP, a new workflow for parameter-efficient continual pre-training, which is designed to better transfer knowledge learned from large-scale dataset like Kinetics 400 to AQA tasks. Second, we propose a 3D adapter module to be inserted into 3D CNN for the first time. And third, we introduce PD40 dataset, a new AQA benchmark for the vision community to assess different actions performed by Parkinson's disease patients. And fourth, our extensive experiments show significant enhancement in current AQA methods using our continual pre-training approach. This figure compares the traditional transfer learning approach using previous AQA methods with our proposed PECoP transfer learning. As you can see in part A of the figure, the traditional method takes a model pre-trained on a general dataset and fine-tunes it with a specific AQA task. In part B, our PECoP approach introduces an additional pre-training step. Here we only update a small set of 3D adapter parameters with domain-specific unlabeled videos, while the rest of the model weights stay frozen. Actually, this extra pre-training step helps to reduce the domain gap between the general task and the specific AQA target tasks. Here you can see a more detailed overview of our PECoP pre-training and fine-tuning pipeline. In the first stage of pre-training, we use supervised learning with a domain general dataset such as Kinetics 400. This stage gives the model a broad understanding of different actions. Next, we move to in-domain SSL continual pre-training. Here, the model learns from domain-specific data by training only the adapter layers, which is shown as the green layers within the I3D model. This stage helps the model to start understanding the nuances of the AQA actions we are interested in. Finally, we fine-tune the pre-trained model on the AQA target task using state-of-the-art AQA methods. In this slide, we're looking at our 3D adapter module, which has a bottleneck structure designed to significantly reduce the number of parameters. We've integrated this module within the inception modules of the I3D model. Empirically, we found that this spot for the 3D adapter works best and gives us the top performance. Now let's begin our exploration of the experimental setup with our proposed PD40 dataset. This dataset contains 2,931 videos from 30 Parkinson's disease patients. As you can see, this dataset includes a range of tasks such as gait, hand movement, leg agility, and figure tapping, and each task is scored on a scale from 0, which indicates normal subject, to 4, indicating severe symptoms according to UPDRS standards. In addition to our PD40 dataset, we also evaluate our model on other benchmark AQA datasets that have been extensively utilized by previous AQA methods. These benchmarks include MTL AQA and fine diving for diving action quality assessment, as well as Jigsaw's dataset, which is used for evaluating surgical skills such as suturing, knot tying, and needle passing, as you can see in the sample videos. Here we're looking at our baselines, which represent the aesthetic health art methods in action quality assessment. Actually, these baselines are utilized in the fine-tuning stage, and the pre-trained ITRD model, which is enhanced through our PECoP method, serves as the backbone for each of these baselines. Here you can see our results on benchmark dataset. In table 1, we show our results on the MTL-AQA and Jigsaw's datasets, comparing our baseline methods MUSTL and core with enhancements by PECoP and a recent continual pre-training workflow named HPT. As you can see, our PECoP method consistently improves results across all tasks, especially on Jigsaw's. On the other hand, HPT actually decreased core's performance, likely due to overfitting because it's larger parameter updates. In table 2, we present results on the fine diving dataset. Here we compare the core and TSA methods with and without the PECoP enhancements. TSA plus PECoP showed a slight improvement over TSA alone, but it's the combination of core plus PECoP that achieves state-of-the-art performance on this dataset. In table 3, we are looking at our results on the PD40 dataset. What stands out here is the improvement when we integrate PECoP with both USTL and core frameworks. While HPT also brings improvements, the real story here is about efficiency. PECoP managed to achieve nearly the same performance boost, however, with much lower continual pre-training and storage overheads. This table highlights the efficiency of PECoP compared to HPT in terms of trainable parameters and the overall pre-training cost. PECoP requires approximately 1 million trainable parameters, which is significantly less than the 13 million required by HPT. Also, it achieves this with only 8 epochs of training, which is half the number needed for HPT, and results in a model size of about 4 megabytes compared to 54 megabytes of HPT. These numbers actually underscore PECoP's effectiveness as a resource-efficient continual pre-training strategy. In our abolition study illustrated here, we explored different self-supervised learning methods used in the second stage of PECoP to determine which would be most effective for action quality assessment downstream tasks. The results are presented in Table 5, where VSPP and SSL methods achieved the highest performance. Also, Table 6 shows the impact of our PECoP approach on the PD40 dataset using the R3D18 backbone. With PECoP, we see an improvement across all tasks of this dataset. This figure compares the performance of different pre-training strategies on AQA tasks. DOMG, or Domain General Pre-training, employs pre-training on a Domain General dataset like Kinetics 400, while DOM-S, or Domain-Specific Pre-training, focuses on Domain-Specific Self-Supervised Pre-training on target data. HPT plus BN is batch norm tuning, in which it fine-tunes only the batch norm layers of a pre-trained model. As you can see, PECoP consistently outperforms the other approach across all tasks. On the other hand, batch norm tuning doesn't do as well on the Jigsaw tasks. This indicates that it may struggle with tasks that have a large domain gap. In summary, PECoP has made significant strides in the area of AQA. We have achieved efficient knowledge transfer from large video datasets to AQA tasks, enhancing performance while being parameter efficient. Our evaluations across multiple AQA datasets have shown PECoP's effectiveness and its advantage over traditional continual pre-training methods. Also, PECoP has contributed to resource optimization by cutting down on both storage needs and training costs. Looking ahead, we focused on addressing the balance between complexity and efficiency, ensuring our models capture complex features without underfitting. We are also planning to evaluate PECoP across different backbones beyond 3D CNNs like transformers. And finally, we aim to expand PECoP's application to different vision tasks such as action recognition and few-shot learning. Thank you for listening and your attention.